All right, here's our lecture for 3/5, Tuesday. We have just this week, and then we have spring break, so y'all get excited about that. A couple of caveats. I have been sneezing all day, and so I am stopped up and or may continue to sneeze during this video, so be prepared for that. In addition, you may catch glimpses of my bathrobe, because that is what I'm wearing because it's chilly in our house. What we're going to cover today is we're going to talk about everything you need to know for the quiz on Thursday, and then we're going to work some problems as part of that review. And I was originally going to kind of have the lab report before that, but I want to talk about that kind of at the end once we've covered what we need to cover to make sure everybody understands the material and what the scope of the quiz is going to be on Thursday. So with that, let's just outline briefly what is going to be on the quiz, just as far as what's in the book and what's going to be on. And we're just going to kind of go through. I think we've had very uneven performances from kind of the whole class on a lot of things, and so I want to just make sure I've done my part so that if things don't go so well, as you're preparing for your quiz, you'll be able to go back and see very clearly what you should be studying for that. So it's just going to be section 9.1 through 9.2. Okay, and that kind of seems like that's not very much, but it's actually plenty. Okay, and so I'm just going to kind of go through. All right, so you need to know what Boyle's law states. So we will say, what does it say? Okay. And then you will need to be able to work problems such as ones that involve subbing into this equation. Okay, we're going to work some just to make sure everybody's clear on that. Okay, you're also going to need to pay pretty good attention to this because some of these calculations are involved in your lab report, and that will, be more difficult if you don't know how to work with this equation. All right, and then 9.1.2 we have Charles' law. And V1, T1, E2, T2. Okay, you also need to know what it states. Okay, and I recommend that the way you approach this is that you are understanding what these things are saying. Okay, what is the concept that they are attempting to, get through about the physical world that maybe they didn't know before the 18th century, right? So we need to know that what happens when temperature goes up. Okay, so we don't, you can always answer the question is, if I increase the temperature, what will happen to the volume if pressure is held constant? Okay, so you can plug in two temperatures and an original volume and then see what happens to the second volume. Okay, you can always go through the math to figure out what conceptually it's saying, but you should understand that as well. Okay, And we're going to work through at least one of these problems that is representative of what we've got going on here, so you guys understand what we're going to see on the quiz. I don't want anyone to be surprised by anything that shows up there at all. Okay, we will touch on Avogadro's law. What does it say? And volume is equal to K. And we'll come back to this and explain what that is. All right, so then we have, this is 9.1 various, and this is 9.2. Not worried about the subheadings really so much. Okay, we'll have this pressure absolute is equal to the pressure atmospheric. I feel like I'm missing a letter there. Atmosphere. No, I got the P and the H backwards. Sorry. Plus the P gauge pressure. Okay. And we'll come back and talk about that as well. All right, and then the ideal gas law. And this is kind of the summary of the others. And essentially it is PV equals nRT. Okay. And this ideal refers not to the law, but to an ideal gas. Okay, and that gas. Well, we'll come back to that. Let me finish going through these. Sorry. Okay. I think that is the summary of what will be on the quiz. Okay, so not a lot of vocab. Okay. Although being able to talk about these, Boyle's law, Charles' law, that's going to be important, okay? I hate to, just make you memorize something about, this one's about pressure and volume, this one's about temperature and volume, but it's actually important to associate these names with the laws and not just know that, yeah, somebody did something and there's pressure and there's temperature and there's volume, okay? So make yourself some flashcards. Make sure you guys can answer questions about which is which. You got 1, 2, 3, Avogadro, who we're familiar with from his number. Okay, so that should actually help you with this one. All right, so let's get into what we are going to do with these. Okay, so Boyle's law, what does it say? It says that as pressure goes up, volume goes down. Okay, this is exactly what we did with our syringe portion of our experiment. Just a reminder to Caroline to bum somebody's data on that and pretend that you were in their group all along. Okay, but what happened, right? As you guys loaded up books or whatever you were using for weights, what happened? That syringe volume, that fixed amount of gas got squished tighter and tighter until you really couldn't make it go anymore. Okay, and so as that pressure increased, and we'll talk about some of those calculations in there, as we get into the lab report section. As pressure increased, that volume decreased, and you can plug in numbers and play around with that and see what happens when you've got a certain pressure and a certain volume. You double the pressure, what happens to the volume? Okay, it has to go to half. Okay, And there's some nuance here about making sure you're measuring you're plugging in the absolute pressure, and that you're taking atmospheric pressure into account. I don't know that I explicitly called that out in the lab report, but it was brought up to me, and so that may be some tweaking we have to do for future classes for sure, but also to make sure everybody's working those things correctly and thinking about it clearly for their lab report. Okay, we'll work some problems here in just a minute. Charles' law, what does it say? All right, so this is sort of the hot air balloon area. All right, so that as temperature goes up, volume goes up. Okay, so when these are arranged this way, as one of these goes up, this guy's got to go down so that these remain equal. Well, as one of these goes up, the other one goes up, or vice versa. This goes up, that goes up. That's what has to happen for these to have that direct relationship. So these have got an inverse relationship, because we could replace this with a constant. Okay? And so as this goes up, that's got to go down to keep this thing constant. Okay, well, same deal here. Okay, if I put a 2 up here, I've got to double this down here as well to keep that ratio the same, which would be constant. Okay, all right, and this is where you add kinetic energy in the form of heat to a gas. It's going to increase that volume. So you crank up the flame on the hot air balloon and it fills it up. Well, it's not adding gas so much in there as it is causing the existing gas in there to expand and to fill that balloon and push harder on the inside skin of that balloon so that it takes up more volume with less gas and creates a buoyancy effect. And it basically floats up through the air then, okay? We'll work some problems there as well. Avogadro's law, what does it say? It says that a volume is based on a certain number of moles, okay? And this has the understanding that this is at standard temperature and pressure. Okay, and I think we talked about that in chapter 8. Okay, and what were they? I want to direct you to the page. Give me just a second to find standard temperature and pressure here. I'm sure you guys have already found it, and so I'm just behind you. I'm actually going to pause you so I can find it. And it was just on the next page, but I started looking backwards. All right, so standard temperature and pressure. What do we have there? We have 1 atmosphere and 0 degrees C. Okay, and we worked through some of those in our homework. I sent you guys the answers for those, so you should have some of this, but it doesn't hurt to go back over it. Okay, and so what does that mean? That means the volume of a certain number of moles has this constant here. And mostly what we're working with is 22.4 liters is equal to 1 mole of gas at atmospheric pressure. Okay, and just to remind you here that something like O2 is going to equal 22.4 liters, so 1 mole of O2, okay, as well as some monoatomic gas, so like let's say just a helium. 1 mole of helium also equals 22.4 liters. Okay, so get this, make sure you're really super clear on this in your mind, okay? Even though this has got double the number of atoms of O2 than this one does, they're both one. This is 1 mole of those O2 molecules. An O2 molecule, this, acts in an ideal gas sense. It acts just like 1 unit. Okay, so we'll just call this 1 unit. All right. Now he kind of looks like a little alien. Give him some eyes. It's kind of E.T. Now we're totally messed up on that one. So F2, which is another diatomic one, right, acts as 1 unit. Whereas that's equal to 1 unit of helium, which is just an He. Okay, so don't get confused about the number of atoms. That doesn't matter. The number of molecules matters. Whether that molecule is a single helium or a double oxygen, double fluorine, S8 molecule, whatever it is, molecules of H2O. So 1 mole of H2O is kind of what we've been talking about, but this is a real important application of it here. So that H2O acts as 1 unit. Okay, that's we see them acting, and I think this Avogadro's law stuff was actually part of what led him to the concept of the mole, and he didn't kind of have the pre-existing mole unit in his mind, and then he was like, hey, this is also true for gas. I mean, I think this idea that, wait a minute, even though we've got more mass here in, let's say, an H2O versus an H2, it still acts the same way in that we have this set of number of molecules that keeps the same volume. Okay? All right, so just keep that in your mind there. Ideal gas law is where he talks about standard temperature and pressure. And so just to remind you that this absolute equals atmospheric plus the gauge. So if my gauge reads 100 kPa, and I ask you what's the absolute pressure, all you got to do is plug that into your equation here. Okay, so we know P absolute is whatever the atmospheric pressure is, which is what? You guys know, 101.325 kPa. And what's my gauge reading? Well, it's reading 100 kPa. So my absolute pressure is actually 201.325 kPa. And what does that mean? That means that if we took that gauge out into outer space, right? And we saw somebody like him, our alien friend, our gauge would then read this. It would literally stop reading this and it would read that, because at that point it would be reading the absolute pressure, because there is no atmospheric pressure. Okay? And the absolute pressure is what doesn't change, no matter what your atmospheric pressure is around there. Okay? Okay? Good deal. So make sure, if you have to, just memorize that. Okay, just memorize this. Don't let points slip away from you because you could have just worked it pretty straightforwardly. Okay? And then we have the ideal gas law. And this, like we said, is sort of the summary law or the summary equation of all the other ones. All right, we've got pressure in whatever units. We've got volume in whatever units. We've got number of moles and whatever, well, that's always going to be the same thing. R is going to match the units. And then T is temperature in Kelvin. Okay, gotta be in Kelvin. Okay. So we had some difficulty on a number of the quizzes about when to put things into Kelvin. This is always got to be in Kelvin. Your numbers just won't work. If you do Celsius. But if you're doing something that's got a difference in temperatures, so you're subtracting a final temperature minus an initial temperature, you don't have to worry about Celsius versus Kelvin. The degree size is the same, and so you can pick either one you want. If it's given in Celsius, just do it in Celsius. If it's given in Kelvin, just do it in Kelvin. So that's not a problem. All right, so let's push on through and work some of these problems. Actually, why don't y'all get your homework out, and I want to work through. I had a number of questions about both 23 and 28, so let's go ahead and work those while we're thinking about them. And then we'll jump right back to the quiz. I know I didn't have that on my little list there, but I think you guys will be okay. And especially since this is fresh, you can mark up your paper. And again, we just be real conscientious that you may not remember very well what you didn't understand or did understand. So try to make clear notes on your homework if you missed something or couldn't get an answer or whatever. Now, I have not graded your homeworks yet, but I want you to go ahead and be looking at yours so that I don't have to write every one of y'all a note, because there's 11 of y'all and just one of me. And so if I can just kind of check off your homework that you've put forth the effort and that I know you have marked it up because we've gone over it in class, that will make me feel a lot better that I've done my part to help you guys understand. Okay, so all right, let's look on, if you got your book, page 252 is where we are.
Sorry. I apologize.
So Voyager 1 space probe leaving our solar system forever sent back data. It determined the composition of the atmosphere of Titan, Saturn's largest moon. Atmosphere consists of 82 mole percent. Okay, so why is that important? Okay, well, because the partial pressures is based on the number of moles out of the total number of moles that any particular gas. Come on, focus here. That any particular gas has there. Okay. Doesn't want to focus. Come on. Hit a clue. There we go. All right. So if something was just based on its mass percent, like remember we did the percent mass calculations. Yeah. So that wouldn't work. Okay, because of Avogadro's law, where it's saying that any number of moles is always going to have the same volume. Okay, so this is all going to be in moles. So just zip right to that. And sometimes it'll be given to you and sometimes it won't be. Okay, so for right now, he's just going to give it to us because it's kind of the first problem in here. So 82 mole percent. And we'll just shorthand that to 82%. Argon is 12%. And methane is 6%. All right, so first let's make sure 82 and 12 is 94 plus 6 is 100. So that's 100%. Okay, good. We don't have any missing elements there. All right, so total pressure is 1.61 atmospheres. And this could be anything. That could be millimeters Hg, that could be kPa, it could be PA, whatever. It doesn't matter. All right, so we want to determine the partial pressure. Okay, so for nitrogen, it's 1.61 times 0.82, and that gives us an answer 1.32 atmospheres. Argon 1.61 times 0.12. 0.19 atmospheres, and then methane. All right. Now, to be careful and rigorous, you'd want to take this and you want to add them back up. So we'll say 1.32 plus 0.19 plus 0.036. And I got an answer. That's not right. I'm sorry. This should be 0.096. Did I do that right? 1.61 times 0.06. 0.096. 6 there. It's 1.61 times 0.12. 0.192. Now, does this add up? 1.32 plus 0.192 plus 0.036. 1.548. I'm getting different numbers than I should. Hold on. All right, sorry about that. And that's why we see it's important to check, okay? Because for some reason, I was changing this number when I was transferring it over here. All right, so now I've corrected this, and they add up to 1.61 atmospheres. So, an excellent object lesson in why we need to be checking our answers to make sure that they're correct. Okay, so that's number 23. It's as straightforward as that. And maybe they get a little more complicated than that. I'm not super familiar with all the different ways we can test partial pressure, but we got a minute to talk about that before our test. So just take that, correct that if you had that wrong on anything on your homework there. Now let's look at number 28. I expect this is going to be a little bit more difficult because I got more feedback on this one. All right, when zinc reacts with sulfuric acid, the reaction products are zinc sulfate and hydrogen gas, according to this equation. That's sweet of them. They provided it for us. All right, and of course we want to make sure, first of all, that it's balanced before anything else goes on. Okay, so let's look at that. How many zincs do we have? One on the left, one on the right. How many H2s do we have? One on the left, one on the right. SO4, we got one on the left, one on the right, so we are balanced. All right. So I would almost make it a habit to write a note that, yep, balanced, we checked it. Okay. All right. So we're going to have to be real careful here. I have not solved this before, so once again, you're going to get to see me solve this. This is not me just writing down something I've got on another sheet of paper here. So let's figure out what we got. So we always want to define our variables and sort of record the pertinent information. All right, so 184 milliliters of H2 is collected. So that's a V, that's a volume. We don't know whether it's in the right units or whether we're going to have to adjust it, but we know it's a volume. Okay, now we've got pressure. It's equal to 757 millimeters
Hg. Again, we don't know if that's going to be the right unit or not. And temperature is equal to 28 degrees C. How many grams of zinc are consumed? Oh, man. All right. So a question that doesn't even seem related to what we've been given here. Okay, I had a couple of notes that were, I am not even sure how I should get the right answer, which I can appreciate. But let's think this through. All right, so we have this equation, and I'm going to drop off the states of matter here, just in the pursuit of making it a little bit clearer. Okay. All right, so what do we know? We got 1, 1, 1, 1. We got a 1, 1 to 1 to 1 mole ratio. All right, so we don't have a whole lot of stoichiometry we've got to do there, other than to know that it's a 1 to 1 ratio. All right, and so we are in the partial pressures here, so we must have to figure out. First thing I'm going to do is I'm going to go look this up. And again, I haven't worked a lot of these, so I'm not exactly sure what the fast, super efficient approach is. Okay, so when you're confronted with this is the kind of procedure you should be going through to try and solve it. Okay, so if we look back in our section, you should note, all right, so we got 9.3.1 there. Then we got 9.3.2. Flip over to 246 here. Let me make sure. All right, so here's the key that's going to give me an idea of where I'm going to look first. Now, this may not pan out, so you guys are going to have to kind of bear with me. Assume that 184 milliliters of H2, I'm back on page 253 looking at the question, of H2 is collected over water. All right, now we have a section that you should have at least read through at some point, collecting a gas over water. I don't know how much we actually talked about this, so this may partly be my fault if you guys are confused about this, but sometimes you just got to work through something, okay? So what do we do? He notes that water vapor pressures at different temperatures are listed in Appendix A, Table A4. So let's flip back there and figure out what we've got going on for our vapor pressure there. And that's on page 390. What's our temperature? We're at 28 C. And we're in millimeters Hg, which is the same as torr. All right, so millimeters Hg is equal to torr, something you need to figure out. Okay, we've talked about it, but it's not super easy there. All right, so we're going to say H2O vapor pressure is equal to 28.38 torr. All right, so what do we do with that? And so it looks like, if you look at the top of 247 there, we take the total pressure to the atmospheric and we figure out what part of that is the water vapor pressure and what part of it is the vapor pressure that is made up of our gas. Okay? So what do we have? We have a P total is equal to the P of our water, vapor, and our, in this case, H2. Okay, and remember that's just because anytime you've got a situation like is demonstrated right here, right? This water there's water vapor going on all the time right here, and it's evaporated and filled that. And so we can't just forget about it. Okay, we can't just forget that there's water vapor in there. And so we've got to account for it. And thankfully, we've got a table that tells us at any given temperature what that amount is. All right, so our P total we know is 757 torr, or millimeters Hg. All right, and so that's 28.38 plus our H2. And then we do our subtraction, and what do we get? 757 minus 28.38. All right, so the pressure we got to keep in our minds is of the H2, and it's 728.62 torr. Okay? All right, now, what do we do? Now we have a volume. We've got a corrected pressure. We've got a temperature. And we are looking for how many grams of zinc are consumed. Okay, we can't answer that yet because we're going to get this. And then we're going to go back and compare stoichiometrically. Ooh, there's a word. Try playing that in Scrabble. You can't do that. It's just, see, that was a trick because there are too many letters. Don't play that in Scrabble. All right, so now we've got a PVT. We know R is a constant. So we're going to solve for our number of moles of H2 that this must be. Okay, so we're going to have PV equals nRT. All right, so let's flip back now. And I know this is a lot of steps, but this is kind of what you need to be doing as you're working through here. Okay, so this is not abnormal to be looking things up as we go. All right, so flip to 235 now. And let's figure out which of these R's is going to work the best. Okay. We've got torr. We've got Celsius. We've got milliliters. So which one of these is going to be the best? Well, let's look for the one that's in torr, or millimeters Hg, and we really have only got one there. Okay, it's the 1, 2, 3, 4, 5, fifth one there. So we'll use R is equal to 62.36 liters torr over mole Kelvin. Okay, which is a good reminder that we have not converted our temperature yet. Okay, got to be vigilant about that. Otherwise, your numbers come out entirely wrong, and you won't even be able to check it. Okay, so what's our pressure? We've got 728.62 torr. What's our volume? Note that this is in liters, so we need to convert that to liters. So we'll say 184 milliliters. What's our conversion? 1,000 milliliters to 1 liter. So that's 0.184 liters. is equal to N. Well, that's what we're solving for. R, we said, was 62.36, and I won't write that whole unit again. And then T. So let's come over here, and we'll just say T in Kelvin is equal to 273.15 plus 28 to 90 up to 301.15. Sorry about that. Okay, that's K. So 301.15 K. All right, and then very quickly we're going to tap that into our calculators here. And we do 728.62 times 0.184 divided by, open parentheses, don't forget to do that, 62.36 times 301.15, close parentheses. Boom. All right, so my number of moles I have is 0.007. Just for accuracy, we'll do 0.71 moles of H2. But we want to know how many grams of zinc are consumed. So how do we get to grams? Okay, remember it's grams to moles to grams. Okay, where are we? Well, we're already here. So we got to go through moles and then the grams. Okay, so we'll set that up. 0.0071 moles of H2. Okay. Here we have, looking back up here, remember we said it was 1 to 1. So 1 mole of H2 to 1 mole of zinc. And now we got to go back to grams. Okay. And so then we have 1 mole of zinc is equal to, what's our molar weight of zinc? 65.4 grams of zinc. All right, and we just multiply. So we should have 0.467 grams of zinc are consumed. Okay, so let me check that to make sure that's, right. Oh, cash money. That's what I'm talking about. 0.467 moles is, excuse me, 0.467 grams is our correct answer. Okay? So, what are the concepts? If it's collected over water, you need to subtract, you need to look up and then subtract that partial pressure of water out, because it's taking up some of that area in that, in that test tube or beaker or whatever you got collecting it over water. Then just use that adjusted pressure, and then you just work it as an ideal gas law. Okay? So, remove H2O partial pressure. And then solve as gas law problem. Okay, so it's really just plugging in, and I guess we could say do stoichiometry if required. Okay, so something like this could very easily show up as a multi-step problem on your test. Okay, so go ahead and do the hard work of figuring out where you went wrong, if you went wrong. Okay, and make sure you can work problems. Okay, it's not. I would love if somebody said, "Hey, you know what? I went ahead and I tried to do 29, and I couldn't get that one right either. Could I see some work for that?" I would love to work that problem and send it to the class. Okay, I'm not going to do that just on all these problems because I've got a ton of things I got to do. Okay, but I welcome you guys looking into this and testing yourself by pulling out some of these problems and seeing if you can get the right answer. And you'll find that, once you've worked these things, you'll get to the quiz and you'll be like, oh man, this is super easy. Okay, if you have done the hard work of going through, figuring out what you know, what you don't know. Okay, if you can't solve another problem, but you feel like you understand this one, you may be a little bit misinformed about your ability to do it. Okay, if you understand it, you will be able to work whatever kind of problem is given to you. So feel free to test some of these other ones. I don't know how many more we're going to work from this particular section. May work a couple more just to make sure everybody's got it. But we got to do 9-4 and work some of those as well. All right, so these are your homeworks. And now let me work at least one from each of the other ones. And so you guys will be clear on how to work those. All right, so let's pull some of these. All right, so something even straightforward like, all right, number 2. Let's just do that one on page 251. All right, gas with a volume of 3.5 meters cubed is at 2.275 bar. All right, so what have I done already right here besides allowing my camera to get out of focus? I have distilled this sentence down into the facts that I need to solve this problem, okay? And I find that helps clarify what I need to do if I just go ahead and write my variables and then what they are equal to, okay? You don't have to do that, whatever. But I find that that's helpful for me, and that's our V1. Okay, the volume is reduced. That means this stuff is the before, and then is reduced means you're transitioning now into the after. So that's my V2. Okay, 1.25. While the temperature is held constant. Okay, so that's important. Temperature is being held constant, so that means we're just worried about this. So we're just worrying about new gas pressure. All right, so we should be able to just recall Vp is equal to V2P2, and then just plug in. Now, does it matter what our units are? Not really. As long as we remember that if these units are the same, then these units will come out to be the same. So we should just have a straight 3.5 meters cubed is equal to 0.275 bar, 1.25 meters cubed x. Okay? Divide both sides by 1.25. All right. And so we should get 0.77 bar. Okay, and just to make sure, what do we say? As that pressure goes up, the volume goes down. So is that the relationship we had? volume went down, so pressure probably went up. Oh yes, it went from 2.275 to 0.77. So excellent. All right. So not a whole lot else to do with the Boyle's stuff there. All right. So on a Charles. All right, let's look at 14. Okay, this is probably as complicated as a Charles law is going to get. Yeah. Okay. Well, hold on, wait a minute. It's not 9.2 is ideal gas law. Sorry, we didn't even work a specific Charles law. Trying to find one that was. I guess we could look at 3. Okay. So gas is at a volume of 2225 centimeters cubed. Okay. Pressure is equal to 655 torr. Temperature is 37 degrees C. Gas is first cooled to where the temperature is negative 15 degrees C. Pressure is constant, so we can see that our volume is going to change. All right, so we'll actually label that. We'll just say volume change. All right, and then what happens? Then the pressure is decreased to 603 torr. While the temperature is held constant. What's the final volume? All right, so let's just take this one step at a time and figure out what's going to happen here. Okay, so if the temperature is held constant, if the temperature is changed and the pressure is held constant, we need the equation that relates V and T. Okay, and that's V1 over T1 is equal to V2 over T2. Okay. Again, you need to be familiar with those. And also the math will come out exactly the same as long as you can flip them. All right, and so that doesn't matter, but as long as you do both sides. All right, so what do we have? We have 2225 centimeters cubed, and again, our units don't so much matter as long as they are staying the same, over T1. Well, what's the problem here? We need to do this in Kelvin, and so 273.15 plus 310.15 K. So what's this one? $258.15 K. And now we're ready to rock and roll. Okay, make sure you're lining up the befores and the afters. And then, so we know there's a V2 here, and we're not sure what it is yet, to 258.15 K. All right, so now we cross multiply, and what do we get? We get 2225 times 258.15 is equal to 310.15 X. So what are we going to do? Divide 310.15. And we get 1851.95. Okay. And so now we've got to decide what our next step is. All right, and so then which one is held constant? Temperature is then held constant. And so we know that there's going to be a volume change again, except this time it's the pressure that's changing and the volume that's changing. So temperature is held constant, so we can forget about that now. All right, so now that means it switches from this one, which was a Charles law. Now it also has become a Boyle's law. Okay. All right, so then we just take this and we say we need a VP, V1P1 is equal to V2P2. And so now this is our V1P1. All right, so we have to treat this like one problem and work everything. And then we treat this like one problem and work everything. All right, so whereas this was situation 1 and situation 2, now because we're treating it like a separate problem, this is situation 1, and now our answer is going to be situation 2. Okay? Not that that really matters here. Just know that that's okay if this is 1 and 2 and then 1 and 2. All right, so what do we have? We got a volume 1, 1851.95 times pressure 1. What did we say it was? 655 torr. And our volume 2 is what we're looking for because we know we've changed our pressure to this. Divide the whole thing by 603. And what do we get? V2 is equal to 2933 centimeters cubed. Okay. And again, none of that matters as far as units, as long as you're not switching units of a particular one. Okay, so we can solve this with any kind of units. They'll all work out as long as we're not switching from torr to kPa without doing some sort of other conversion in here. Okay, that'll mess things up. All right, make sure you're getting Kelvin as well. All right, let's just work a. Did I promise to work anything else? Well, work an ideal gas law. We sort of did a little bit of that in our homework. Let me see if I can find a Avogadro's law one. Which section was Avogadro's law? Was it in 9.3? No, it can't be because it's going to be on our quiz. Yeah, it's actually 9.1. Yeah, we won't work an Avogadro's one. That shouldn't be too much of a problem. I think you just need to know that at standard temperature and pressure, 1 mole equals 22.4 liters. Alright, I warned y'all. I made it almost an hour without sneezing. Okay, well, very quickly, I guess we'll just work one more problem. Although number 28 is going to serve you pretty well in that capacity, but can't hurt. Sorry, guys. Okay, so let's look at number 16. I think that'll be a worthy endeavor for us. Number 16, what do we know? Weather balloon is filled with 275 liters. And our gas is helium. And autofocus. Okay. Temperature is 29 degrees C. I'm just going to go ahead and convert that. You don't want to risk forgetting something because that's such an easy thing to do, to forget. Okay. So now I'm going to go ahead and cross this out so I'm not tempted to use it. All right. And then pressure is equal to 765 millimeters Hg. And I'll write torr here so we can remember that. Okay. Okay, so we know volume can vary since both pressure and temperature vary with altitude. How many moles of helium are in the balloon? So what is that? Well, that's N. All right, so right now, this is a simple PV equals nRT, and we just need to make our R decision. Okay, so let's flip back, and y'all see if you can figure out which of these R values it should be before I write it down here. Look at all your units you're given. All right, so for my money, I'm going with liters torr mole K, that fifth one again that we used in our homework. And I'm just going to all right, so then we plug in 765 millimeters Hg, 175 liters. N is what we're looking for, 62.36. And temperature is 302.15 K. Do our multiplication and solve for N. And what do we have? We got 765 times 275 divided by 62.36 divided by 302.15. All right, so we've got 11.17 moles. All right, what's the second part of the question there? At an altitude of 10,000 meters, the temperature is 221 K. So now we've got a new temperature, so we're going to call that T2, just to keep it straight. 221 K. And the pressure, you tricky trickies, kPa. All right. So now we want to know volume equals question mark. Well, maybe it's not so tricky because now we can just write a whole new equation of PV equals nRT. 25 kPa. We're looking for a volume. The number of moles. Okay, it's a weather balloon so that they're stuck at that. That can't go anywhere, so we just pull that down. R, we're going to need a new R because we've got now kPa. We'll solve for liters, that's fine. So we'll just use this first one. 8.314 liters kPa mole K. Well, now we just need our new temperature, 221. Okay. And so then it's that multiplied, divided by 25. 314 times 221 divided by 25. We should have volume should be 820.6 liters. All right. Good deal. I think that's about going to wrap us up for what we need to do for tonight. Study, work some problems. Go back and make sure you can work the homework problems from last week, from before we did our lab. And then come on in on Thursday ready to knock out a quiz. And it's just a regular size quiz, 30 points, so no freaking out about it. But come in ready to work that out, and then we will finish out Chapter 9. Oh, very quickly. You've probably forgotten how to do lab reports, okay? Because it's been, I don't know, 3 months since we did one. All right, so that lab report, March 19th. Okay. Guys, I know you got spring break. I know you are probably traveling and visiting and just unwinding from the hard work you guys have been doing for the last 2 months. I will be doing some of the same, okay? But you must start working on this lab report because Friday is what? It's already the 8th, so then you only have 11 days before it's due, okay? So just make sure after you rest up, maybe Tuesday, Wednesday, really start getting back into it, okay? Check in the handouts. Look at your old lab reports and what my criticisms were on there. Hopefully constructive criticisms. Okay. And start gathering it together. Okay. On Thursday, I will try to work through some of those equations and the pre-lab stuff to make sure everybody's on the same page with that. Y'all feel free to get together and talk that through, though. Okay. Don't just wait on me to go through that. You guys have the ability to communicate with one another pretty easily. So just put a reminder on your calendar. Put a reminder on March 12th so that you can say, hey, whoops, I've got a week until that lab report and I haven't done anything. So I need to get moving on it. If you need me to look at stuff, I'd love to do that. I would. Let me see how my schedule looks before you send me a whole lab report, okay? I don't know how much time I'm going to have to give full criticism of them, and I think we've done 2 now, so it should be a little bit clearer what we're aiming for. You've got that rubric, really get into that, get back to that, and just, put in the time. Put in the time to do a full write, do the whole thing, write the whole thing, and then go back and edit. And then go back and edit, and then go back and edit. Sometimes that's the only way to really get what you need out of a lab report. All right, we'll talk to you guys soon.